Hello guys, and welcome back to the channel. It's been a while and I will just get into it. In today's video I will be implementing the linear regression algorithm. So we are basically going to be coding together, and my inspiration is from this book. Let me take you guys to the very cover page. Wait a minute. Yup, the Elements of Statistical Learning. If you're into machine learning and data science, this is like, people like to refer to it as the Bible of data science and machine learning. So it's a good foundation, and it's a book that I recommend. So the good thing is that it's freely available online. The authors of the book have made it open and freely available. So just go online, search for the Elements of Statistical Learning, the Elements of Statistical Learning, and you can download it from their website, from Stanford University. Yep. Yeah, on this website you can download the book PDF from here. Okay, so let's get back to the book. The very first chapter in the book is an introduction that of course you should read, but the meat of the book starts in the second chapter, and that's where we're going to be focusing on page 9. I hope when I put page 9 it takes me to actually page 9. No, it doesn't. So I have to manually scroll down. Yep, and we are here. So this is it. The second chapter is the overview of supervised learning. If you watched my previous video, I gave an introduction to the concept of machine learning and how that in machine learning we have sort of two branches, supervised and unsupervised, okay? And the book starts off with focusing and discussing supervised machine learning. When it comes to supervised machine learning, the idea is that we're making some type of predictions, and these predictions could be qualitative or quantitative values. Check out that video, we wouldn't go back into that. But the sort of main idea in this chapter is that when it comes to supervised learning and making predictions, there are two foundational approaches. That's what it's called. Two simple approaches to prediction. One is that you have this least square method. The other one is that you have what is called the nearest neighbors method. And these two approaches are pretty foundational. Why? Because the many other complex approaches to predictions are usually some type of variation of these two simple approaches. Okay, so when we're talking about neural networks and we're talking about support vector machines and whatever other complex models that are out there, really boils down to tweaking one of these two simple approaches. So in machine learning and in data science, it is extremely important that you have a good grasp of these two simple approaches, because it's foundational for you to understand all the other approaches. Okay, so the very first one that I would be focusing on implementing on the right screen is the Jupyter notebook. Here is where we'll do the implementation. On the left we have the linear models and least square. So this is the first one, and the primary equation for this kind of model is that y hat means the predicted value. So we have the actual value and we have the predicted value. The actual value is y, and the predicted value is called y hat. So y with the little cap on it. So it says y hat is equal to b0 hat plus summation j going from 1 to p xj b hat j. Okay, if you take a look at this equation, it might start to look familiar to you, right? Do you remember your equation of a straight line, where y is equal to mx plus c? Okay, in the equation of a straight line, y is equal to mx plus c, where m is the slope of the line, right? And c is the y-intercept, if we are in two dimension, where we started off as in elementary maths. That same idea is what is the same thing that's happening here in the linear model, where y hat is b0. b0 is the intercept, or what we call in machine learning the bias of the model. And here bj is the slope or the gradient of the line. The interesting thing is that when we have a prediction problem, we have the actual y. So we have the actual y, this one, y is usually known. We have x is known because you have usually a training set, and your training set is basically your x and your y. What we do not know are the coefficients. We don't know the slope. So assuming that, if we assume that the data set that we're working with is generated from a linear model, a linear model, think simplistic, like straight line, if we're in two dimension, we know our x, we know our y, but we do not know our y-intercept, and we do not know our slope or gradient. And the whole task that we have is to find this missing piece of the puzzle. So find the slope and find the intercept or the bias. This equation 2.1 can be generalized into what we have in the equation 2.2. If you read what the authors wrote here, it says often it is convenient to include the constant variable 1 in x, okay, and then include b0 into a vector b. So this b hat would basically contain both the intercept b0 and the sort of the gradient or the slope bj, and then into x we'll add the variable constant 1, so that when we multiply this, it's basically the same thing. This is just for convenience. And then this is the interesting page where I would focus on for the most of this video. The question is, how do we find b? Remember, we have y, we have x, but we don't know what b is. And how we find b is that we use this method called, it's written here, the least squares approach. And the whole thinking here is that if I have the actual value of y and I have the predicted value of y, I want to make the difference between the actual value of y and the predicted value of y as low as possible. So the best b, so the best coefficients, the best slope and intercept that we can find is the one that makes the difference between the actual y and the predicted y as low as possible. In short, that can make it 0. If you can find such values of the slope and the y-intercept that can reduce the difference between the actual y and the predicted y to 0, then we're good. So then we define this function here, which is basically the difference between the original y, the actual y. You see that this y doesn't have a cap, so this is the actual y, and the predicted y. I know you're saying like xtb and you're wondering what is xtb. Remember, xtb is simply the predicted y. So we are saying that the residual sum of squares, which is the error, is simply the actual y minus the predicted y. And for convenience, we make that a quadratic function by putting the square there. Okay, if you open up this, it gives you 2.4. So 2.3 and 2.4 are basically the same thing. And so here it says that what we want to do is that we want to differentiate this function 2.4 with respect to b so that we get this. We have the function, it's not that complex if you study a bit this part of the text, but it gave me a hard time and I advise you to stay with it a bit longer. So the idea here is that we have this function y minus y hat is a function of b. Okay, it's a function of the gradient and the intercept. Depending on how we set the gradient and the intercept, it would affect the values that we get here. And we want it to be at 0. So we want it to be as little or even like just 0. We want no error. And so if you differentiate the function 2.4 with respect to b and set it to 0, we can then make b the subject of the formula and get 2.6. Okay, I might be bad at explaining that because that is not the main aim of my video, but yeah, I advise you to read that whole chapter and get a better understanding. The aim of the video today is to implement this. So we want to be able to implement b and to make predictions with b. So let's get started. In order to do that, just give me a second. Yes, in order to do that, we need some libraries. Okay, so we're going to be doing it with NumPy. So we need to import NumPy as np. You also see that, at some point we need to take the inverse of some metrics. So we do from NumPy dot linear algebra, we import inverse. This function is implemented in scikit-learn, and I would like us to compare our implementation here with the implementation in scikit-learn. So I would import the linear regression module from scikit-learn. So from scikit-learn dot linear model, yep, import linear. Do I get some help there? My autocomplete is not acting 100 today. Okay, well, I think that is linear regression. Yep. Oh, yeah, we made a mistake there. From scikit-learn.linear model. Yep. Okay. So that's that. Let's implement the first one. So we want to have two functions. One is that we fit, and the other one is that we predict. Okay, so in this case we get an x and we get a y, just like so, because that's all we know. All we know is our x and our y. And what this function is supposed to return the coefficients b. Okay, so the first thing here, just following the same implementation that we have here, is that we need to do x transpose, right? So x transpose will be, we use the NumPy function. So NumPy dot transpose x. Okay, so that's going to be our x transpose, and then we have to do x transpose times x. So let's call it x transpose x. We are doing matrix multiplication of x transpose and x. Okay, so we have this part. We've done x transpose, we've done x transpose x, and now we should take the inverse. So x transpose x inverse would be, remember that we have this inverse function here from NumPy, so we're just going to do the inverse of x transpose x. Right, what are we missing? Let's do the right hand side. So x transpose y, we need to do the right hand side, x transpose y, and we have x transpose y to be equal to, that's matrix multiplication going on there. So we have NumPy dot matrix multiplication of x transpose y. We already have x transpose here, and we multiply it by y. Okay, so we have the left term x transpose x. So we have x transpose x inverse here. You see it there, and we have x transpose times y here. And now we can return our coefficients as NumPy dot matrix multiplication of these two terms, and we say return b. Now when we want to fit, we have some x train, and we need also the value of our b, right? And if we want to make a prediction, all we need to do is just to do x transpose times b. So y is just x transpose b. And so we put here y underscore pred to be equal to let's just call that np dot matrix multiplication let's just call it xb and say return y underscore pred. Good. So now let's define another function and call it test, and this our text function is going to take x tests is going to take, no, let me put it at x train. Okay, it will take x train, it will take x tests, and it will take y. And what it's going to do is that it would fit so our b would be equal to fit, and then it would predict. Control C. Of course, this is going to be x train, and this is going to be this. Ba-da-dum. Okay. It should return result. And let's test that out. So let's say we have a train test that is just a NumPy array. You know what? Let's have, let me copy some here. So let's say we want to test with this. We have a train case, so we have 1 2 3 4 5 rows and two features or two columns. So we need to have the intercept b0, and we have b1, and we have b2. So we are looking for 3 values, and this is y, and this is y test. However, remember that in this part of the book we talked about having a constant variable 1 in x, because we want to include b0 into the vector of coefficients. So we need to include this constant 1. All right, so we need to include the constant 1. And so what we can do is that we modify x train and also x test and include some 1s. We include some 1s. So let me show you what that looks like. Let me print train with bias. You see, we just include a constant 1 to help us find the right value for the bias or the y-intercept if you're in 2 dimension. Okay, and so now we can, let me also print this one for you to see. You see that the constant 1 has been included. And so now we can test the function. So we just run test with x test with bias, y test with bias, and okay. Let's look back at the textbook. So B, I think we were supposed to transpose x here, and we forgot to do that. So let me include this line here, and run. Okay, so the error is in the input into the test. So we need to put train test y, and so the train should come first. That was the error on my part. So it should be train test y. Yes. So with this implementation, the predicted value for y when we have 6 and 7 is 22.8. So let's try to see what answer we get when we use the scikit-learn library. So we define the function linear regression, linear regression, and we do linear regression dot fit, and we just put our train and y, and then we can do pred. We can then predict linear regression dot predict, and we predict. I see I made a mistake there. That should be a point, not a comma. We predict x underscore test. Let's print that. Voila, and it's the same answer with the library. So you see that it's not so difficult to implement the linear regression, just following what's given in the textbook. What we've implemented in this video is what is called the closed form solution, meaning that we have a definite straight way to find the values of our coefficients. The problem here is that sometimes you can end up with a matrix that does not have an inverse, and in that case it's impossible to find the solution in this closed form, as they say, and we need to go through what's called an iterative approach. So in the next video I would implement also the linear regression model using the iterative approach. I hope you found this one interesting, and I encourage you to give it a try to implement the linear regression yourself. It's x transpose x all inverse times x transpose y, and after that you have your coefficients that you can use to multiply all your incoming x to make predictions for your y. Thank you for sticking around in this one, and I will see you in the next video. Till then, keep having fun with data. Bye.